All right, today we are going on a journey, a pretty wild one actually. We're heading right to the edge of theoretical physics to try and wrap our heads around one of the most mind-bending ideas out there, the actual shape of our universe. And it all kicks off with this one statement that, let's be honest, sounds pretty much impossible to understand at first.
Yeah, see what I mean? This sounds insanely complex, right? It's like something out of a sci-fi movie, a secret code for the universe. The core idea here is that the very fabric of our reality, space-time, is something way, way stranger than we ever thought. So the big question is, what does this even mean?
So to crack that code, it really all boils down to this one single question. And that's our mission for today. We're going to tackle this thing together, building the whole idea from the absolute ground up, piece by tiny piece. And I promise by the end, that crazy-sounding statement, it's actually going to make a whole lot of sense.
Okay, so think of this like we're about to climb a huge mountain. You don't just start sprinting up the cliff face, right? No way. First, you set up base camp, you get your gear in order, you understand your tools. And that's what we need to do here. Before we can even think about something as complex as a Calabi-Yau manifold, we've got to get a handle on the absolute basics. Like, what even is a space in mathematics? And believe it or not, it all starts with the simplest idea you can possibly imagine. A set. Seriously. Just picture a bag of dots, or points, or whatever. There's no structure, no lines connecting them, you can't measure how far apart they are, they're just a collection of things. That's it. This is our blank canvas.
Okay, canvas is blank. Now let's add our first layer of detail. This is where we get something called a topological space. All we're doing here is deciding which points are neighbors. We're not measuring anything yet. We don't know if they're a foot apart or a mile apart, but we know which ones are close to each other. I love the analogy of knowing who lives on your street. You know who your neighbors are, even if you've never measured the exact distance to their front door.
The next step is simple. We add a ruler. Now our space becomes a metric space. We're taking that fuzzy idea of closeness and making it totally precise. So now, not only do you know who your neighbors are, you know it's exactly 52 feet to their mailbox. We can measure the distance between any 2 points. Suddenly, our space has a rigid, solid structure.
So, this difference is absolutely key. You gotta get this. A topological space, that's like a stretchy rubber sheet. You can pull it, you can squish it, you can bend it all over the place. As long as you don't actually tear it, the neighborhoods, the connections between points, stay the same. But a metric space, that's like a rigid city map, printed on cardboard, with a scale in the corner. Distances are fixed, angles are fixed, everything is absolute. This distinction is, well, it's everything for what comes next. All right, base camp is packed up. We've got our tools. Now we start the real climb. We're about to move from these abstract ideas of points and distances to shapes that actually start to resemble the world we live in.
And this leads us to one of the most brilliant ideas in all of math, the manifold. Here's the core concept. A manifold is any shape that looks flat if you zoom in close enough. The perfect example, the one we all experience every day, is the Earth. Right now, where you are, the ground looks flat, doesn't it? But we all know we're living on a giant curved sphere.
And that right there is the key insight. It's so cool. The math works for any of these curved shapes. A sphere, a donut, you name it. Even really, really weird ones. If you just zoom in far enough on any single spot, your view becomes basically identical to a flat piece of graph paper. It's locally flat.
But then, you zoom out, and you see the bigger picture. That little flat patch of graph paper was just a tiny piece of the puzzle, an illusion of your limited perspective. In reality, all those tiny flat pieces are stitched together perfectly to create a much larger globally curved shape. And that idea, locally flat but globally curved, that is the very soul of what a manifold is.
Okay, we are getting so close to the summit now. We can see it. We have our manifold, this beautiful, curved space that looks flat up close. To get all the way to a Calabi-Yau, all we have to do is add a few final, very specific, you might even say elegant, layers of structure on top. Now, this part looks a little technical, I know, but stick with me. It's just a sequence of upgrades. Think of it this way. First, we upgrade the building blocks. Instead of regular numbers, we build our manifold with complex numbers. This just gives it a richer, more powerful geometry. Then, we add a special kind of ruler, a Hermitian metric that's tailor-made to work with those complex numbers. And for the final step, we add one last crucial rule about symmetry. Once we do that, bam, we have what's called a Kähler manifold.
Look, we're not going to get bogged down in the equations here. The important thing is the concept.
Each of these steps is like adding a new law of physics to our little universe. Switching to complex numbers, that lets you build things like rotation right into the fabric of the space itself. That special ruler, the metric, it just makes sure that all your measurements of distance and angles behave in a really consistent and, well, beautiful way. And that final symmetry rule, that's the masterstroke. It locks the whole thing into a state of perfect geometric balance.
And with that final condition locked into place, that's it. We've done it. We're at the summit. We can finally turn around and see the breathtaking view, the very thing we've been climbing towards this whole time.
So here it is. This is a Calabi-Yau manifold. It's the beautiful, intricate shape you get when you apply all those conditions we just talked about. And that last bit of jargon, vanishing first Chern class, it has a really profound meaning. It means the space is Ricci flat. Now careful, that does not mean it's flat like a sheet of paper. It's incredibly curved. But it means its curvature is perfectly balanced. For every bit that curves inward, there's a corresponding bit that curves outward, canceling it out. And this perfect balance is exactly what physicists were hoping to find.
So now, let's go all the way back to the beginning. Let's look at that quote again. Suddenly, it's not some alien language anymore, is it? We know what a Calabi-Yau is. We know it's built from complex numbers. This statement isn't just a random physics postulate. It's a profound suggestion that this specific, highly structured, beautifully balanced mathematical object could be the literal shape of our reality.
So, why does any of this matter? What's the big takeaway? Well, it all connects to one of the biggest ideas in physics, string theory. String theory, which is one of our best shots at a theory of everything, pretty much requires our universe to have more dimensions than the ones we see. But, and here's the kicker, those extra dimensions aren't big and stretched out like ours, they're curled up, unimaginably small, into these incredibly complex little shapes. And what shape is that? You guessed it, a Calabi-Yau manifold. The idea is that at every single point in the space around you, there could be one of these tiny, intricate shapes just humming away with the fundamental rules of the universe.
And that leaves us with a pretty staggering final thought. If this is right, then the specific geometry of these tiny shapes could determine everything about our universe: the strength of gravity, the mass of an electron, all the fundamental constants of nature. So the final question is, if our universe really does have these tiny hidden dimensions curled up into these beautiful shapes, what other secrets of reality are waiting to be found, hidden inside their intricate folds?